Hello, everybody. This is Bert Dixon here presenting today on lesson 3.1 and 3.2 in our statistics textbook. And so 3.1 is on measures of central tendency, which is the mean, median, and mode. These are terms that you may have seen before, possibly in a high school class. Mean is just the average, so it's the sum of all the values divided by the total number of values. When it's a sample mean, we denote it with as x bar, x with a bar on top, and so that would be if we, have a larger population, but we've just collected data from a sample of that population. However, if you are using the entire population, if you have data on every single person or object in the population, then it's called the population mean, and it's calculated the same way, but it's pronounced mu. So we use the Greek letter mu to denote the population mean. So that's the only difference between x bar and mu, is that x bar is for a sample and mu is for an entire population. A median is the middle number in a list of data. And so if you put all the values in order, and if there's an odd number, you just go to the middle one. If there's an even number of items, then you just average the two that are in the middle, add them and divide by 2. And then the third measure is the mode. The mode is the value in the data set that occurs most frequently. And so we'll go ahead and take a look at this example. We have several employees at this small company, and they have various salaries. And so the first thing we would want to do is put the data in order, and then this list is already in order here. And so now we just count how many items there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So there's 25 items. So if we go to the 13th item, that's 42,000. There should be 12 items above and 12 items below. Yeah, so 12 items above and 12 items below. So our median is equal to 42,000. And just for future reference, if you weren't given the list in order, if you were just given this list, some of you may already know how to use spreadsheets. If you don't have a lot of experience with spreadsheets, it's still pretty easy to at least put the numbers in and let the spreadsheet sort them in order for you. So if you open a sheet, either Excel or Google Sheets, either one will work fine. You can just type in the data. Now mine are already in order here because I took them from the list that's there. But if let's say here, let's put the 250,000 at the end, and the 21,000 here, just so I can show as a sample how you would sort these items to put them in order. So you just select all the data, and then click on Data, Sort. And we have, you just tell it what column. So we're sorting values in column A from smallest to largest, and I just say OK, and so it puts them all in order from smallest to largest. If I wanted it the other way, I would go Data, Sort from largest to smallest, and it sorts them from largest to smallest. So that's a convenient tool to use. It works the same way if you're using Google Sheets. So if I go to a new spreadsheet and I paste my values in there, let's see, I'll probably have to grab them from Excel again. copy. Okay, so now they're sorted from largest to smallest. And if I go to data, sort, this is telling me I can sort directly column A, or if I want to put in a specific range, then that's usually what I do is sort range, column A, and then from A to Z. And so if we sort those now, put them in order from smallest to greatest. Okay, and so that helps you for finding the median, definitely. And now back to our example. So it says find the mean, median, and mode. So we found the median. To find the mean, we just need to add all these values and then divide by 25 because there are 25 items. And so back to my Excel sheet, if I just go underneath the list and I type equals, every time you want to do some kind of a formula, you just type equals, and we'll type the word sum, parentheses, and now it's going to sum all the values that I drag across. So if I drag across all these items and close the parentheses, notice it filled in the addresses A1 to A25, press enter. And so now I know that the sum of all that data is 1,481,000. So so that's the x1 plus x2 and so on all the way up to x25. We're going to divide by 25. That's going to give us mu, because this is the whole company. We didn't miss anybody. So this is a population mean. And so that we said added up to 1,481,000. And then if we divide that by 25, and that came out to be 59,240. And then the mode is the most frequently occurring value. Again, it's nice to go back to the sorted list because we can just look for repeats there. And the only repeat I see is 32,000. So the mode would be 32,000. If there was another item that occurred, let's say 3 times or 4 times, that would be the mode. So in this case, this is not, the mode is not really telling us much about this data set because there are not very many repeated items. Okay, so that's how you would calculate each of those by hand. Now, you can use the spreadsheets and you can use graphing calculators also to find mean, median, and mode. And so since we have the Excel spreadsheet here, I'll go ahead and show you that. So again, to type in a formula, you just type in equals, and we're going to put in, I think for mean on Excel it uses average. So we select the word average, or just type the whole word average, parentheses, and I want to make sure I don't select that 1,481,000. I'm just going to select this data and click enter, and it gave me 59,240. That's the same answer that we got when we did it using the calculator. And then mode, same thing. I would type an equal sign, mode, M-O-D-E, parentheses. Now this is looking for, let's see, returns a vertical array of the most frequently occurring repetitive values. And so I think that's the one we want. I'm just going to type mode and then again drag across these cells and close the parentheses. And that tells me the mode is 32,000, which matches the answer we got when we looked at our list. Okay, so those you need to know how to calculate these statistics by hand, but it's nice to be able to use the spreadsheet, especially when you have a large list of numbers, to check your answers and it's good to know how to do it both ways, but you will be required on some of the test problems to show your steps, to show what you did to get the correct answer. So don't just rely only on the spreadsheet and on the calculator. Just to show you quickly on the calculator, if I go to Stat, press the Stat button, and then Edit. Let's say I put in a list of numbers, or so, sorry, you might already have a list of numbers there. So first I want to show you how to clear it out. So what you do is you go up arrow until the list name is highlighted. Do not press delete, press clear, enter. If you press delete, you're going to delete your whole list. So highlight the list name and then press clear, enter. And then let's say I have the values 10, 15, 16, 16, 16, 25, and 38. Okay, so out of those values, if I wanted to calculate the mean or the average, I can go to Stat, slide over to Calc, one variable statistics. And there's list 1 is where our data is, and then we don't have a frequency list, so we're just going to go down to Calculate. And it tells me X bar is 19.43. So that's the average of that short list of numbers that I just typed in. The other statistics that are given there, you don't need to worry about those yet. We will learn how to use some of those shortly. Okay, so right now all you would need is the X bar, and it also gives you the median is 16. The calculator, I don't believe it does give you the mode, so you have to look at the mode. Is easy enough to get on your own, but this gave us the average and it gave us the median of the list of data. Median was 16. Okay, so you can use the graphing calculators, you can use Excel spreadsheets to calculate these for large data sets, and also just to check your answers when you're doing homework problems. Okay, now it's asking which measure most accurately demonstrates the central tendency of the data. And so this, we have these 3 items, and depending on the data set, sometimes the median, sometimes the mean, sometimes the mode most accurately describes the data set. Now in this one, notice that we have most of the values are under 100,000. In fact, all but 2 are under 100,000, and then we have 2 that are quite big, 120,000 and 150,000. Whereas the rest of them are all kind of clustered around, 40, 50, 60,000, around that range. And so what happens is when you have some really large or really small values like these 2, they tend to skew the mean. And so the mean in this case is not probably the most descriptive, because it's suggesting that our the center of our data is probably around 59,000. But it's actually, when we look at our data, we have, like I said, a lot of values in the 30s, 40s, and 50s. And so in this case, the median of 42,000 is probably a better way to describe our data. And so I would say, to answer that question, I would say the median demonstrates the central tendency of the data the best. So I'll write here the median since the 2 highest values skew the mean too much. And then also I put a note here that there's a whole list. So in this problem, we considered the mean, the median, and the mode. but we decided on the median was going to do the best job of demonstrating the central tendency. So how do you know which one to pick? On page 128 in your text, there's a blue box that describes when to use each one. So when is the mean the best? When is the median the best? When is the mode the best? And then there's another one called the mid-range, which we'll talk about right now. But I just wanted to make sure you were aware that on page 128, they have these thorough descriptions of which measure tends to be the best for certain types of data sets. Okay, and then we did see the mid-range there as one of them. So the mid-range is the average or the mean of the lowest and the highest values in your data set. So if you take the high and the low and add them and divide by 2, that gives you the mid-range. And so on that same chart, they tell you that the mid-range, some things about the mid-range. The mid-range is easy to compute. It gives the midpoint of the highest and the lowest value, and the mid-range is affected by extremely high or low values in the data set. So if the data set has one or the other, either a few really high or a few really low, then that's probably not the best measure of your data set. And in example 2, we're going to look for the mid-range of this data set. And so first we need to put them in, or identify which one is the highest and which one is the lowest. So it looks like 10 is our lowest and 34.5 is our highest. So the mid-range then is going to be 10 plus 34.5 divided by 2. And if you put that in your calculator, that is 22.25. And in general, since some of our data items go to 1 decimal place, it's our statistics are measures of central tendency, like the mean, median, mode, and mid-range. We want to use 1 more decimal place than what is displayed in the data. So since some of the data items have 1 decimal place, I'm going to go ahead and go to 2 decimal places for our mid-range. And then next we have the concept of a weighted mean. So a weighted mean would be used whenever certain data items are given a stronger or weaker weight, depending on what their significance is. The best example I can give is calculating grade point average. If you just took all of your grades for your classes and added up the grade points and divided, if you had, let's say, 5 classes and you divided by 5, well, that would mean that each of your classes has equal weight, which when you're in middle school and high school, all of your classes do have the same weight. So, a PE class, a math class, a science class, art class, they're all the same weight. That you get the same number of credits for every class you take in high school. So it was easy to calculate your GPA in high school because you just took all of your grade points and then divided by 5, and that gave you your grade point average. If you had 5 classes, or if you had 6 classes, you would divide by 6. But in college, your grade point average, the weights of each of your classes depends on how many credits they are. So a 1-unit PE class shouldn't carry as much weight as a 4-unit math class. And so the grades are weighted according to how many credits that course is worth. And so when you're calculating your grade point average, first let's convert the letters to numbers. So a B is a 3, an A is a 4, a C is a 2, a B is a 3, and an A is a 4. And so what we're going to do when we calculate this, what it's showing is you multiply the weight times the value for the first number, the weight times the value for the second number, and so on and so on. And then we're dividing by the sum of all of the weights in the bottom. And so when we calculate our GPA, grade point average, we're going to have 4 times 3, so that's the weight times the grade, plus the weight 3 times the grade 4 for the English class, plus the weight 3 times the grade 2 for the Spanish class. Sorry, I wrote 4. That should have been a 2. And then the weight 4 times the grade 3 for chemistry, and the weight 1 times the grade 4 for PE. And then what we're going to divide by is the sum of all of the weights. So that's these. So 4 plus 3 plus 3 plus 4 plus 1. And when you put that in your calculator, you want to make sure you have all of that in parentheses and all that in parentheses. So on the, let's see. Okay, so to put this in on my calculator, I would start with parentheses, and then I would type 4 times 3 plus 3 times 4 plus 3 times 2 plus 4 times 3 plus 1 times 4. Close the parentheses, then divided by, now I need new parentheses for the bottom, 4 plus 3 plus 3 plus 4 plus 1. And so when I complete that division, I get 3.06 repeating, and so for grade point average, typically you get it 2 decimal places, so 3.07 would be our, if we rounded that to the 100th place, that would be 3.07. Okay, so that completes the 3.1 video. So now you can take out your student notes for chapter 3 and start at the beginning and then go through the end of the page that says properties for mean, median, and mode. So through lab problem 3. And then after you're done with lab problem 3, then go ahead and press play again, and you can watch the 3.2 portion of this video. Okay, so go ahead and pause now, and then come back when you're ready for 3.2. So in the last lesson in 3.1, we learned 4 different ways of finding the middle or the center of our data. And so sometimes the mean, sometimes the median, sometimes the mode, sometimes the mid-range describes our data the best. If we had to pick one single number, depending on how the data is dispersed, we choose one of those to represent the center of our data. Okay, so now in 3.2, what we're going to talk about is how spread out our data is. So that's called variation. So when we measure variation, we're talking about how is it spread out. Okay, is the data really tightly dispersed so that there's not much variation, or is it really spread out and has really high values, really low values, and scattered values in between? And so variation is what measures that. Okay, I think we've already talked about range. Range is just the highest value minus the lowest value. And then one of the ways we measure the spread is using the population variance. And so if we're working with an entire population, then the variance is, it's always a positive number because it's the variable that we use for variance is sigma. That's lowercase sigma. You might be familiar with sigma notation. This is a uppercase sigma, whereas this is a lowercase sigma. And so we use sigma squared for variance, and this is the formula. So basically what this means is when we do x minus mu, so x is our current variable or our data item, and we subtract the mean. So for each data item, we do the data item minus the mean, and then square it. And then the next one, we do data item minus mean and square it. And we do that for all the data items. So if we had 20 data items, then we would be doing the number minus the mean squared 20 times and then adding those all together. So this uppercase sigma means sum. So we're adding them all up. And then we divide by n, which is the number of items. and that gives us the variance, or sigma squared. So that gives us the variance. And then if we take the square root of that, if we take the square root of the answer we got for sigma squared, that gives us what we call the standard deviation. So the standard deviation, think of what deviate means. Deviate means how does it change, or how does it differ? And so the standard deviation tells us, on average, how far away is each data item from the middle, or from the mean. And so we're always comparing. When we talk about standard deviation and variance, we're always talking about, compared to the mean, how spread out is our data. And so this measure, the standard deviation, tells us the average distance from the middle to a data item. So if we had, let's say, our mean for a data set was 36, and we had an item that was 40, well, that is 4 units away from the mean. And so the standard deviation tells us, on average, how far are they? We might have another data item that is 56, and so that is 20 items above the mean. And so we have one item that's really close to the mean, one item that's really far. On average, how far are our data items from the mean of 36? And so that's what standard deviation measures. It's measuring the average distance from the mean to each data item. Okay, and so we'll go ahead and calculate both of those statistics, the variance and the standard deviation for in this example, sorry, we have 2 brands of paint, and this tells us on average how long the paint lasts in years, and so or months actually. Yeah, yes, these are in months. So we'll do brand A by hand, and then I'll show you how when we do brand B, we'll use a calculator and a spreadsheet, so you can see how to do it both ways. Okay, but keep in mind, when you do this on a test for a small data set like this, I would ask you to show all the steps of calculating the standard deviation and the variance by hand. So that's what I'm going to demonstrate here. And maybe on a problem that had a larger data set with 20 items or something like that, then I would have you do that with a spreadsheet or a calculator. So you do need to know how to do it both ways, how to do it by hand and how to use technology. Okay, so and you'll notice that when you do these in Connect Math, there sometimes will be a button that says export to Excel, and so it'll take the data items and put it in Excel, so then you can do some calculations in Excel. Okay, so what we're going to do for this is we're going to have a list of our variables, and then what we have to do is do x minus mu, which is the mean, or the average, and then we're going to square it. So we're going to have x minus mu squared. We're going to do that for each item. So the first thing we need to do is calculate our mean. And so for this data set, if we add 10 plus 60 plus 50 plus 30 plus 40 plus 20 and divide by 6, we have 6 data items. That is 291.67, or sorry, that is not 261.67. That is, let's see, 10 plus 60 plus 50 plus 30 plus 10. Or no, that's actually a 40. Not a 10. 40 plus 20. I got 210 divided by 6 is 35. So 210 divided by 6 is 35. So that is, our mean is 35. So for brand A, our mean is 35. So we're doing basically x minus 35 for this column. And so this is 10. If we do 10 minus 35, that would be negative 25, and then we're going to square that. And if you square negative 25, you get 625. We're going to do that for each data item. So the next one is 60, and we do 60 minus 35. That is also 25, and then it's positive this time, but when you square it, it turns out to be the same number. And then 50, then we'll do 50 minus the mean, and that is 15, and 15 squared is 225. Then we'll do 30. 30 minus 35 is 5. 5 squared is 25. See, these are not too difficult to do by hand. 40, you would do 40 minus 35. Sorry, this one should have been actually negative 5, but when you square it, you get 25. And then this one is still 5, 25, and then 20. We do 20 minus 35 is negative 15, and negative 15 squared is 225. Okay, and so those are all the calculations, those are all the columns that we're going to need. I'm going to shrink this down a little bit so I have a little bit more room to write. Actually, maybe I'll just move the rest of the text down so we have more room to put our totals. And so there we go. All right, so if I total up this column, 625 plus 625 plus 225 plus 25 plus 25 plus 225, I get 1750. And so our variance is 1750 divided by 6, which is 291.67. So that is our variance. And then and that number tells us how spread out our data is. And the standard deviation, which is sigma, is the square root of that. Square root of sigma squared, so that's the square root of 291.67, and that is 17.0. We'll call it 17.1 because these data items don't have any decimal places, so our statistics, we should use one more decimal place beyond. So 0 decimal places, so now we use 1 decimal place for our answer. So this one should have been a 7 as well. So 291.7 and 17.1. Okay, so that is what I got for brand A. So I'm going to put a little subscript A. So we have our variance for A, our standard deviation for A. And now I'll show you how to do brand B. So this the text here that I moved down says both brands have the same mean. So they both have the same mean, but if you look at the data, they're very different data items. These are all fairly tight values, whereas these ones are spread out. It goes as low as 10, but as high as 60, whereas these ones are all in the kind of in the 30s and 40s for the most part. We do have a 25, but they're all tightly dispersed compared to brand A. So that's where the variation will help us. Okay, so now I'll show you how you can use a spreadsheet to do this, and I'll also show how to use a graphing calculator to calculate the standard deviation and the variance. And so I'm going to type in the values 35, 45, 30, 35, 40, and 25. And so then here I'm going to say equals I typed VAR, and it gives me 2 choices, VAR.P and VAR.S. So the variance for the population or the variance for the sample. And so we're considering this to be a population for both of these. It doesn't really say in the problem, but we're assuming this is all the data that exists for this brand. If it is a sample, then we would use .S. But for for this example, we're treating it as population variance. So I'm going to choose .p by double clicking it, and then I drag across the data in rows 1 through 6 and say enter, and it gave me 41.7. So for brand B, the variance turned out to be 41.7. So that's much smaller than the variance we got in, sorry, this is for brand B. The variance for brand B is 41.7, much smaller than for brand A. And then we can also go back to our spreadsheet and say equals, and this time I'm going to type ST and the abbreviate STDEV, so standard deviation. They have, again, .P and .S, so standard deviation for the population is the one we want, and we'll put in from 35, or sorry, from A1 to A6. It's supposed to be A6, so I'm just going to type that in from A1 to A6, enter, and it gave me 6.5. So the standard deviation is 6.5 for brand B. So again, much smaller. So remember what this number 17 means. That means on average, the data items are about 17 units from the middle or from the mean, whereas in brand B, it's only 6.5 units to the middle. So that tells us something about the consistency of brand B. Even though they both have an average of 35 months, brand B is much more consistent. So we can expect if we buy brand B, we can expect it to come somewhere close to 35 years. Whereas with brand A, the average is 35, but we may have really poor performance and get 10 years. We may have great performance and get 60 years. It's kind of a gamble to use brand A, whereas brand B is very consistent, and we can expect, something around 35 years if we buy brand B. So that's where just having things like the average or the mean isn't usually enough to compare data. We need other things to compare, like the variance and the standard deviation. And then I did also mention that I would show you how to calculate the same thing on a graphing calculator. So if you have a TI-83 or TI-84, I will do brand B for this one as well. So after turning the calculator on, there it goes. We go to Stat, Edit, and then we want to put in the data items for set B, which is, remember how to clear. You go up to the title L1 and don't press delete, because that'll delete your whole list. We want to clear, enter. So that clears the list, and then I'm going to put in 35, 45, 30, 35, 40, 40, there we go, and 25. There's my 6 data items, and so now I go to calculate the standard deviation and variance. I go to Stat, Calc, and then one variable statistics. So this is the same thing we did before to calculate the mean, but now we can look at some of these other items that are here. So it says that our so the mean is 35, and then look at S of X and sigma. Sigma is what we want. Sigma is our standard deviation, and so our standard deviation says is 6.45, which would round to 6.5. So that matches what we got using the spreadsheet. And then let's see what else is in here. That's all we need. So it gives you the standard deviation. So to get the variance, you would just square it. So you would take this number 6.45497 square it, and that would give you the variance. So the calculator gives you standard deviation, square it if you want to get the variance. Okay, and then if we're calculating, instead of calculating this variance and standard deviation for a population, if we have a small sample and we're using it to represent a very large population, then we would want to use a slightly different formula. The formula looks identical to what we just used for variance and standard deviation, except we're dividing by n-1 instead of n. And the purpose of doing that is it gives us a slightly larger variance, which gives us an unbiased estimate of what the population variance really is. So we're dividing by n-1 instead of n, and that way it gives us a slightly larger value. And so everything that we did in the last example when we did this table by hand, we would do exactly the same thing. The only difference is at this step right here, instead of dividing by 6, we would have divided by 5. And so here, finding the sample variance and sample standard deviation for these numbers, I'm going to set up a very similar table to the one we just did. And so we're going to have our variable x. We're going to have x minus x bar. Notice we're using x bar, not mu, because it's a sample. And then we're going to square that. And then we'll total them up. And so our numbers are 9, 10, 14, 7, 8, and 3. And if we calculate the average of those numbers, x bar turns out to be 8.5. And so here, if we do 9 minus 8.5, we get 0.5. And then square that, and you get 0.25. Then we have 10 minus 8.5, that would be 1.5. Square it. 1.5 squared is 2.25. And then 14 minus 8.5 is 5.5. Square that, and we get 30.25. 7 minus 8.5 is negative 1.5. Square that, and you get 2.25. 8 minus 8.5 is negative 0.5. Square that, and you get 0.25. And then 3 minus 8.5 is negative 5.5. Square that, and you get 30.25. And so now we add those up. When you add those up, you get 65.5. And now we're, instead of, even though there are 6 items, n equals 6, since this is a small sample that's representing a large population, we're going to divide by 5 instead of 6. And that gives us 13.1. So our variance equals sigma squared, or sorry, not sigma squared, we use S for a sample. So that's S squared. So S squared equals 13.1. And so then our sample standard deviation is S, and that is the square root of 13.1, and that turns out to be 3.6. Okay, so that's the only difference when you're working with a sample, is that you divide by n-1 instead of n. There's also a shortcut formula that you can use for sample variance and standard deviation. You can calculate the sum of squares of all the values and multiply by the value n, which is the number of items. And then then do the sum of all the x's and square that answer. So the difference is here you're squaring the items and adding them up. Here you're adding up the items and then squaring it. So that's the big difference there. And then if we divide by n minus 1, that'll give us the same answer as what we did up here, as this table here. And so mathematically, they're the same, but this just tends to be a little bit easier. And then for the standard deviation, again, you just take the square root of the sample variance. And so we can redo what we just did in example 2, but this time we'll use the shortcut method. So that would look like this. I have my x values are 9, 10, 14, 7, 8, and 3. And so my sum of x values is equal to 51. Then if I do x squared, that's 81, 100, 196, 49, 64, and 9. So I just squared all those x values. Now if I add those up, I get 499. And that's all I need to calculate the variance. So I have n, which is in this case 6. So I'm going to do 6 times, it says the sum of x squared. So 6 times 499 minus 51 squared. So that's the sum of all the x's squared from this part of our table. So that goes there, that goes there. Then we're dividing by n minus 1. So that is 6 times 5. And that adds up to, or comes out to 13.1 for s. And so then, sorry, that's s squared. So then s is the square root of that. And that is 3.62, which will round to 3.6. Okay, so we get the same answers. It's just a generally easier way to do this. So notice that this only works for sample population, or sorry, sample variance and standard deviation. But if we're doing the whole population, we still have to use the full method, like we did in example 1. There's also another measure called the coefficient of variation, and we use that when we're comparing things that don't have the same units. If we want to see which, 2 different samples, which one has more variance, we want to do that as a percentage of the distance from the mean rather than the actual distance from the mean. And so because if you're comparing things with 2 different units, then it doesn't make sense to talk about the variance or the standard deviation. So what we do is we take the sample variance, multiply by 100, and divide by x. So that's what we're doing for samples. Or you take the population variance, divide by the mean, and multiply by 100 for populations. So either way, this is something you can use to compare things that have different units. So for example, in number 4 here, the average age of nurses is 31 years with a standard deviation of 4.5. Then we're comparing that to their salary. So age and salary don't have the same units, but we can still compare which sample has more variation by writing it as a percentage. And so for the we'll use the population for this one. So it's the standard deviation is 4 points. So for this is for age. So for age, it's going to be 4.5 divided by the average 31, and then multiply by 100. And so that is 14.52%. So the that compares the variance to the average, and so that's 14. The variance is 14.52% of the mean. And then for salary, we do the same thing. If we take the standard deviation of 3,500, divide by the average, 42,000, and multiply by 100. In this one, we get 8.33%. And so age has more variance. So remember, variance tells us the spread has more variance than salary at this hospital. Okay, so they have much broader age range of their employees than they do salaries. Okay, and then Chebyshev's theorem also gives us a way of comparing data sets. The proportion of values from a data set that will fall within k standard deviations of the mean will be at least 1 minus 1 over k squared. And so in this one, in this example, the mean is 20. So x bar or mu, we don't know which one it is 20 for this one. And the standard deviation is 2. So according to Chebyshev's theorem, at least what percentage of values will fall between 10 and 30? So our middle is 20. So we're going down to 10 and up to 30. That is within one standard the standard deviation was 2. So this is if this is sigma, if sigma equals 2, then this is 5 sigma and 5 sigma. So both of these values are within 5 sigma of the middle 20. So you can go 5 sigmas above, 5 sigmas below. That takes you to 10 and to 30. And so k in this problem then is 5, because it took 5 standard deviations to get from 20 down to 10 and 5 standard deviations to get from 20 up to 30. And so k equals 5. So then according to this, at least 1 minus 1 over 5 squared. So 1 minus 1 divided by 25 is 96%. So at least 96% of the data lie between 10 and 30. Okay, and then we'll do it again for example B. So this time between 12 and 28. So from 12 to the middle 20, and from 20 to 28, the distance in both directions is 8. So that is 4 sigmas, or 4 standard deviations, depending on whether it's a sample or a population. So 4s or 4 sigma, and so k equals 4. So we'll do 1 minus 1 over 4 squared. So 1 minus 1 divided by 16. That is 93.75% of the data, at least 93.75% of the data lie between, because data is plural, lie between 28 and 12, but so between 12 and 28. Okay, so at least 93.75% of the data will lie between 12 and 28. So this is not telling us exactly how much, it's just saying at least. Okay, and then the last thing we're going to talk about is normal distributions. And so a normal, when we use the word normal, that means it has a bell-shaped curve. So our data, there's a lot of data in the middle and not very much data out at the extremes. And so we have a graphic of that down here. So this is kind of what a bell-shaped distribution looks like. And so we typically get normal distributions when we have a really large sample of data. Like if you calculated everybody's height in the country, you'd have obviously millions and millions of data items. And so when you're measuring something like that, everybody's height, or everybody's wingspan, meaning distance from their fingertips on one arm to their fingertips on the opposite arm, so their wingspan. If you measure or if you look at SAT scores, those are all examples of things that fit a normal distribution. So it generally occurs when you have lots and lots of data. And so in a normal bell curve, 68% of the data values will fall within one standard deviation of the mean. So we see that here. So here's the middle, that's the mean, X bar. So if we go one standard deviation this way and one standard deviation that way, that's why it says X bar plus 1S, X bar minus 1S, because the S stands for one standard deviation. So we're going one standard deviation above X and one standard deviation below X. And so 68% of the data should land within one standard deviation of the mean. And then similarly, if we go out to two standard deviations, notice here it says X minus 2S and X plus 2S. So going from there to there is, I think they put their marker in the wrong place. That should be right there and right there. That's going to be about 95% of our data are going to fall within two standard deviations of the mean. Actually, I'm looking at this. This is their markers should all be in the middle of the bar, so they didn't all end up in the middle of the bar for some reason. But they should all their markers should be within should be to the middle of each bar. And then if you go out to three standard deviations in a normal bell curve, 99.7, so that's almost everybody, is going to be within three standard deviations of the mean. And so if you're thinking in terms of height, I don't know what the standard deviation is for the height of the world's population, but very, very few people make it beyond three standard deviations. So if you're out in four standard deviations, five standard deviations, and beyond, you're in a very small portion of the population. Okay, so we can use this bell curve in this example for SAT scores. So suppose in 2016, the SAT scores followed a bell curve, and the average score was 542 with a standard deviation of 47. Okay, so on this bell curve, now we're saying this is 542, and the standard deviation is 47. So if you do 542 plus 47, that would put you at 589. Or if you do 542 minus 47, that would bring you down to 495. So 68% of your population should have scored between 495 and 589 on their SAT exam. If you did two standard deviations, all we have to do is add another 47, so 589 plus 47. That takes me out to 636, and then middle, so 542 minus, we can just do 495 minus 47. That puts me at let me try that again. 495 minus 47 puts me at 448. And so that is going to comprise 95% of the population would score between 448 and 636 and so on. Okay, so in this problem, it's saying within what boundaries do you expect 95% of the scores to fall? So that is 95% is the one we just calculated. So we'd say between 448 and 636. So again, those numbers came from doing x bar plus 2s equals 448 because it's 542 plus 2 times 47 to get 448, and then x bar minus 2s, which would be 542 minus 2 times 47 to get us to the, this one came out to be 636. And then this one, when we subtract, turns out to be 448. Okay, and then it says what percentage of scores would be above 589. So back to this table, we said, I erased some of this stuff, we said that 68% of the population is going to fall within these two. So what remains? So 100% minus 68% is 32%. So 16% of that is going to be up here, and 16% is going to be down here. So above 589 would only be 16%. So so the answer to this would be 16% of the population. And again, the way I got that is the whole bell curve represents 100% of the data. So if 68% of our data is between 495 and 589, then what remains is 32%. So I cut that in half. That is 16%. So 16% for above and 16% for below 1 standard deviation. And so 16% of the data, or 16% of the scores, I could say, are above 589. Okay, and that completes our notes for 3.3. So now you can go to the next page in your student notes. It was labeled 3.3, but it's actually 3.2, and so you can fix that on your handout. I think these student notes might have been from a different textbook, and that's why the numbering is not always quite accurate, but I'll try to alert you of those things as we go. So you can start at the beginning and work through until the problem's right below the bell curve, and then go ahead and stop there. All right, have a great day, everybody. Let me know if you need help.